Greetings everyone, and welcome to the next video in my lecture series on differential equations. In this video, we will look at the derivative of a Laplace transform. So as you can see, I've already written a relationship here. Let us imagine that we have some function f of t. Its Laplace transform is capital F of s. But what happens when we take that f of t and we multiply it by t to the n? It turns out that when we take our original function, lowercase f, and multiply it by t to the n, that's the same as taking the derivative of the transform with respect to s and doing that n times, and multiplying it by -1 to the n. So let's take a look at why this is. We're going to show that the first, we'll only look at the first derivative here, because once we've done one, you can see how it's going to work. Now, if we've got Laplace transform of just our basic function f of t, then the definition of the Laplace transform says we integrate from 0 to infinity e to the negative st f of t dt. Now let's actually go ahead and take the derivative with respect to s of f. That means we're going to take the derivative with respect to s of this integral from 0 to infinity of e to the negative st f of t dt. But notice that the only term inside this integral that actually has s in it is the e to the negative st. So if we take that derivative inside the integral, we get the integral from 0 to infinity of the derivative with respect to s of e to the negative st times f of t dt. But when we take the derivative, we're going to get the integral from 0 to infinity of, now e to the negative st, take the derivative, we get negative t, and then e to the negative st, f of t dt, and that's just taking that derivative. And if I do a little bit of rewriting here, I'm going to pull the negative out. I'm going to write the e to the negative st next, and then I'm going to put in square brackets the functions that remain, so t and f of t dt. But notice how this whole thing is just negative the Laplace transform of the thing in the square brackets, which is just t f of t. And so we can see here that if we're taking the Laplace transform of t f of t, we're just going to get negative the derivative of the Laplace transform capital F with respect to s. So why do we care? That's always a great question. So let's recall that the Laplace transform of sine omega t is equal to omega over s squared plus omega squared. So if we want to find the Laplace transform of t times sine omega t, then we're just going to take the derivative of that and multiply it by -1. So let's take that derivative. We're going to have a -1 up front. And the derivative of omega over s squared plus omega squared is we're just going to take that denominator, s squared plus omega squared, and raise it to the, basically it's to the -2 power, so square in the denominator. We're going to multiply by a -1 there, and we have an omega, and now we're taking the derivative of s squared plus omega squared, and so we're going to get 2s. And so we get 2 omega s onto s squared plus omega squared, and that's one of the formulas that's on your Laplace transforms sheet. But if you wanted to take then the Laplace transform of t sine omega t, or sorry, t squared sine omega t, then you just take another derivative, the derivative of what we have on the right-hand side here, to get that. Similarly, just scrolling up a little bit here, the Laplace transform of cos omega t is equal to s over s squared plus omega squared. And what that means is then the Laplace transform of t times that is going to be -1 times the derivative with respect to s of s over s squared plus omega squared. And of course this one's substantially more annoying because it is a quotient. And so using the quotient rule, we're going to have the denominator, s squared plus omega squared, times the derivative of the numerator, which is 1, minus the numerator, which is s, times the derivative of the denominator, which is 2s, all over s squared plus omega squared, the denominator, squared. Cleaning that up a little bit, you're going to get negative 1 on the outside, and then our fraction is going to be over s squared plus omega squared, all squared, and you're going to get s squared plus omega squared minus 2s squared. That gives us omega squared minus s squared over s squared plus omega squared, all squared. And then applying the negative 1, that gives us s squared minus omega squared over s squared plus omega squared squared. Similarly, if you wanted to find the Laplace transform of t squared cos t, oh, that should be omega t. I don't know why I didn't put that in. Oops. If you wanted to find the Laplace transform of t cos omega t, then you would just take t squared cos omega t, then you just take the derivative of the result that we just found. Now, using this rule, let's do another example. I'm just going to scroll down here. So using this rule, and again, we're just talking about the first derivative here. So if we take the Laplace transform, oh no, let's write out the full thing. T to the n f of t is equal to negative 1 to the n, the nth derivative with respect to s of capital F of s. We find that Laplace transform of t e to the 7t is equal to, n is 1 here, so it's going to be negative 1, times the derivative with respect to s. We're only doing the first derivative of the Laplace transform of e to the 7t. So that's negative the derivative with respect to s of, and the Laplace transform of e to the 7t is 1 over s minus 7. And taking that derivative, we get 1 over s minus 7 squared. The negative 1 in the denominator is going to become a positive out front, multiplied by the negative 1 out front, and that's going to give a positive 1 over s minus 7 squared. The reason this is interesting is that previously we found that the Laplace transform of, wow, that's a terrible bracket, t e to the 7t we said the Laplace transform of t is equal to 1 over s squared. T to the n is n factorial over s to the n plus 1. Our n is 1 here, and that the effect of the e to the 7t shifts on the s-axis. It makes our s go to s minus 7, and so instead of 1 over s squared, we have 1 over s minus 7 squared, and we get, in a very reassuring way, the same result. That you can consider t e to the 7t either as just t but then shifted, or you can consider it to be e to the 7t and then taking the derivative.